So this is the first video for the topic enthalpy changes. It is quite a large topic and some people get these subtopics confused. So make sure you keep reviewing and keep track of where you are and don't get some of these ideas confused. So the first thing we're going to do today is look at some definitions for this topic, and we're going to look at enthalpy profiles as well, or energy diagrams. We need to understand the definitions within this topic really well, because unless we understand the definitions and be able to write equations for them, we're going to get the calculations wrong later on. So you must try to understand what the definitions mean and be able to write equations for each of these definitions that we're going to look at today. Before we look at the definitions, we're going to look at enthalpy profiles or energy diagrams. And most of you have done these energy diagrams before, so this is a bit of revision, but we must be able to draw these correctly and not miss some details out that students often forget to include. To start off with enthalpy profile diagrams, we need to define what enthalpy means. Enthalpy is very simply the heat change of a reaction at constant pressure. So we often do reactions at constant pressure in chemistry, because often the reaction vessels are open to the air, they're not sealed, so you don't get a build-up of pressure in the container. So most reactions are done at constant pressure in the lab. So this is the definition of enthalpy. Enthalpy profile diagrams are often called energy profile diagrams or energy diagrams, and you would have seen these before at GCSE, I think. So they basically show the change in stored energy or potential energy in a reaction from the reactants to the products. So in an exothermic reaction, like the combustion of methane, so burning methane releases heat, the stored energy of the reactants are higher than those of the products. So when the reactants react together and form the products, there is a loss in energy, and that loss in energy goes into the surroundings as heat. So heat's given out to the surroundings. So this is an exothermic reaction. When you draw an enthalpy diagram, make sure you write a balanced equation of the reactants and products on the relevant lines here on the energy level of the reactants and on the energy levels of the product, and make sure you put state symbols as well. You can see on this diagram that I've included the activation energy for the reaction. So this is the energy that is needed to break the bonds in the reactants before they rearrange and form the products and release heat in forming new bonds. So remember, we put energy into break bonds and then energy release when new bonds are formed. So this shows the change in energy over the course of the reaction. The arrow that shows the activation energy always starts from the energy level of the reactants. When you put energy in to start the reactants gain energy, so there's an increase in energy to form the intermediates or the activated complex. The intermediates then rearrange and form new bonds, and in forming bonds, energy is released. The overall change in enthalpy or change in energy is from this level to this level. So the enthalpy change, the change in heat, is going to be here, and it's negative because this arrow is pointing in the opposite direction to the axis. So when we look at the enthalpy profile or energy diagram for endothermic reactions, like here we have citric acid and sodium hydrogen carbonate or sodium bicarbonate reacting together to give us the salt of the acid, carbon dioxide and water. This reaction is endothermic. The energy level of the reactants are below that of the products, and there's an overall increase in energy in that process. So energy is absorbed from the surroundings to cause this increase. Since the energy is absorbed from the surroundings become colder, so the reactions feels cold if you hold a container that contains that reaction. So these ingredients are actually used in sweets like lemon sherbet. So the citric acid and the sodium hydrogen carbonate or the bicarbonate are in the sweet. So when you eat a lemon sherbet, sometimes it feels slightly cold in your mouth. The important thing here is to notice where the activation energy arrow goes, because a lot of people get that wrong on an endothermic reaction. Often people write this as the activation energy, which is not correct. As we did for the energy level diagram for the exothermic reaction, the arrow for the activation energy always starts from the energy level of the reactants. And in the case of the endothermic reaction, this arrow would be pointing above the energy level of the products. And the reason is we need to have an arrow coming down from the activated complex or from the intermediate energy level back down to the product's energy level, because energy is released in forming the new bonds. So this arrow must go above the energy level of the products. So the arrow for the activation energy then is from the energy level of the reactants as usual to the energy level of the intermediates or the activated complex. Notice also the enthalpy change for an endothermic reaction is positive. You can see this arrow for the change in enthalpy is in the same direction as the axis, so this value is positive. We covered so far the enthalpy profile part of the topic, so you should be able to draw enthalpy profiles or diagrams for exo-endothermic reactions. We're going to look at some definitions now, which are really important to get right in order to get the calculations right later. And we're going to look at some of these definitions within different subsections of this topic. So these are the ones we're going to look at today. So we're going to look at some definitions of enthalpy changes, different enthalpy changes, and it's really, really important that you are able to write equations for each of these definitions and make sure you understand what the definitions mean, because if you don't understand what the definitions mean, you're going to have a hard time constructing what we call Hess cycles later on, or understanding what the Hess cycles mean. So the first one we're going to look at is simply the enthalpy change for a reaction. So this can be any reaction, and we can write a symbol for the enthalpy change of reaction as this, delta RH. So delta means change, R is the reaction, H is the enthalpy. Some books will write it as this. In fact, most books will write it as this, and sometimes simply as delta H, because this is for any reaction. This is not any particular reaction. So the definition of enthalpy change of reaction is the enthalpy change when a number of moles of reactants in an equation reacts to form the products. So the enthalpy change for a reaction refers to an equation. So this equation here has this enthalpy change. The kilojoules per mole is the units of enthalpy change. In this case, the mole isn't really the moles of any particular one of these reactants. If I have 2 moles of hydrogen reacting with 1 mole of oxygen and forming 2 moles of water, I'm going to have this amount of energy released. And we can have enthalpy of reaction for endothermic reactions as well. So when we heat limestone in a limestone kiln to make quicklime, this is an endothermic process. Heat is going into breaking down the limestone, and this decomposes to give us 2 products here. And we have 178 kilojoules needed to break down 1 mole of calcium carbonate to give us 1 mole of calcium oxide and 1 mole of carbon dioxide. So enthalpy change of reaction refers to a written down equation. So they must give you an equation, and then they write the enthalpy change next to it, and that enthalpy change relates to the equation. So in these examples, if I were to have 1 mole of hydrogen rather than 2 moles of hydrogen reacting with oxygen, the value of this will be half of minus 572. And let's say we have 10 moles of calcium carbonate decomposing to give us 10 moles of calcium oxide and 10 moles of carbon dioxide. This would be 10 times the value. So if we're given values of enthalpy change of reaction for given equations for different reactions, we can actually use those values later on to do some calculations. So it's really important to understand what enthalpy change of reaction means in order to use these equations and values correctly for the calculations. The next definition that we need to understand is enthalpy change of combustion. So it has a symbol delta CH, or in some books delta HC. So we have enthalpy and change in enthalpy and combustion here. So the definition of enthalpy change combustion is the enthalpy change or heat change at constant pressure when 1 mole of a substance, so this could be an element or a compound, that's why we use the word substance, undergoes complete combustion in excess oxygen. So here's an equation that shows the enthalpy of combustion of carbon, and for 1 mole of carbon, so this is 1 mole of a substance, yeah, so we've written this as 1 mole of carbon, burning in excess oxygen to give us carbon dioxide, and that enthalpy change is minus 394, so it's exothermic. So when we burn carbon, heat is released, and we release 394 kilojoules for every mole of carbon that is burnt. The equation underneath here is showing the enthalpy of combustion of hydrogen. So you can see I've clearly written the equation for burning hydrogen, and we've written it for 1 mole of hydrogen. So this is 1 mole of the substance undergoing combustion. And burning 1 mole of hydrogen gives us 286 kilojoules. Notice that this equation is very similar to the one I've shown earlier, whereas this is the enthalpy of reaction for this equation. This underneath here is written for 1 mole of hydrogen burning. So this is showing the enthalpy change for the burning of 1 mole of a substance. So this is the enthalpy of combustion of hydrogen. This equation, although it is the combustion hydrogen, because it isn't written as 1 mole of hydrogen burning, would not be considered as the equation for enthalpy of combustion hydrogen. So there's a slight difference, hopefully you can see. Knowing your definitions for different enthalpy changes is really important for doing calculations later. So for example, let's say I needed to know the enthalpy of combustion of hydrogen, and I wasn't given it in an equation, but I was given the enthalpy change for this reaction, and I know this value. I can actually work out the enthalpy of combustion hydrogen by dividing the value by 2, because if 2 moles of hydrogen burns and releases 572 kilojoules, burning 1 mole of hydrogen should give you half the amount of energy. So half of 572 is actually 286. So this is why it's really important that you understand your definitions for enthalpy changes before we do the calculations later. A lot of people don't spend the time understanding these definitions, and they find the calculations harder then. So make sure you do understand the definitions and be able to write equations for these definitions. I've only just noticed that I missed out the half on this equation here, and make a correction on the video for later. So the next enthalpy change that we need to know for today is enthalpy change of formation. So the definition of enthalpy change of formation is the enthalpy change when 1 mole of a substance is formed from its elements. So the enthalpy change of formation has this symbol here. So the enthalpy change of formation of glucose is the enthalpy change as 1 mole of glucose is formed. So I've written this equation here to balance for 1 mole of the glucose from its elements. So here's the elements, the carbon, hydrogen and oxygen that forms the glucose. So forming 1 mole of glucose from its elements has an enthalpy change of minus 1271 kilojoules per mole. So 1271 kilojoules of energy is released when 1 mole of glucose is formed from its elements. So here we've got the equation to show the enthalpy formation of carbon dioxide. So we're forming 1 mole of carbon dioxide from its elements, which are carbon and oxygen, and we have an exothermic process which is minus 394 kilojoules per mole. Now, if you've been paying attention, I've actually shown you this equation earlier. So if you look earlier here, this equation is exactly the same as the enthalpy combustion of carbon. So remember, the enthalpy combustion is the enthalpy change when 1 mole of a substance undergoes complete combustion, and that is minus 394 for carbon. It just happens that this equation is the same as the enthalpy formation of carbon dioxide. So carbon dioxide from its elements, or forming 1 mole of carbon dioxide from its elements, also has the same enthalpy change because it's the same equation. So this is why it's so important you understand your definitions for calculations. So for example, if you needed to have the value of NP formation of carbon dioxide and you haven't got it given to you, but you were given the NP combustion of carbon, well, that's the same value as the NP of formation of carbon dioxide. This is why it's so important you understand your definitions for these reactions. It will help you a lot when you do calculations later on. So we covered in this video the enthalpy profiles for exo and endothermic reactions. So remember to write the equations on the correct places and they're balanced. Make sure you draw the activation energies arrows in the correct places as well. We've also looked at some really important definitions that will be really important for calculations later on, so make sure you do learn those. So you need to know the enthalpy of formation of different substances, so forming one more of the substance from its elements. So NP combustion, which is the NP change when one more of a substance undergoes complete combustion in oxygen, and the enthalpy of reaction, which is the NP change for an equation that's given to you. So this relates to a written down equation, and some of these are related as we've shown on the video. So it's really important you understand those definitions so you can spot those sorts of relationships, which will help you out in calculations later on. What will be really useful before we get to Hess cycles is to practice writing equations to represent NP of combustion for different substances, and to practice writing the equation for NP of formation of different substances. We're not going to do Hess cycles next. We're going to look at other topics within this enthalpy change. We're going to look at calorimetry first, and then possibly we're going to look at the bond enthalpy calculations, and leave Hess cycles last, because Hess cycles is the one that people often find more challenging, although it isn't really difficult if you understand these definitions and be able to write equations for these. And it's only when people don't do that now they find this bit later on difficult, so make sure you understand these now.